Hello and welcome to Risk-Informed Decision-Making for Earthquake Early Warning. My name is Gemma Cremen, I'm from UCL, and I developed this presentation in collaboration with my colleagues from UCL, EU Centre, BRGM, University of Strathclyde, and the National Observatory of Athens. Now we all know that the last step in the process of any earthquake early warning system, be it a regional or an on-site approach, is the decision module, where information from the incoming event is used to make a decision on whether or not an alert should be issued so that people can take protective measures before the shaking from the earthquake hits them. However, current decision modules make decisions based purely on seismological information, neglecting to consider engineering-related consequence predictions that may be more informative for decision-making, particularly in terms of the built environment. And they also fail to consider diverse stakeholder preferences towards different types of losses and therefore towards different types of decisions that need to be made for an earthquake early warning system. So the aim of this particular project is to overcome the limitations of current earthquake early warning decision modules by developing a novel method for risk-informed earthquake early warning decision-making that specifically integrates earthquake engineering-related procedures for seismic performance assessment with multi-criteria decision-making tools. Now, what do I mean by earthquake engineering-related seismic performance assessment procedures? Well, an example of this type of procedure is the FEMA P58 methodology for individual buildings that was developed for the US and is used in a later application of this presentation. But the idea is that we can translate a ground motion or a series of ground motions into its effects on the built environment in terms of metrics that are interpretable to stakeholders, like repair costs, repair times, and casualties. And these are metrics that stakeholders can use to make decisions based on. So let's look for a second at a hypothetical case of multi-criteria decision-making for triggering earthquake early warning related actions in a school. Now, the overall objective in this case is to manage earthquake risk for the school. And we can imagine that a stakeholder might be interested in the following criteria. That is, maximizing the safety of people in the school, maximizing school productivity, and maximizing public satisfaction. And the first requirement of us as modelers is to translate these criteria into quantitative metrics or indicators. So we can think of maximizing the safety of people in the school as minimizing casualties. We can think of maximizing school productivity as minimizing the number of downtime days of the school. And we can think of maximizing public satisfaction as minimizing school downtime days and also minimizing the repair cost of a school after an event. And it's the value associated with each of these metrics for a particular action that we can take for an earthquake early warning system, and the importance of each of these criteria or indicators to a stakeholder that will determine which particular action is taken for an earthquake early warning system and an incoming event in our method. So once we've identified the criteria of interest to the stakeholder, as well as all possible actions that they could take with an earthquake early warning alarm, we can represent this information in the form of a consequence matrix, where each column of the matrix corresponds to a different criteria of interest and each row corresponds to a particular action of interest, including the possibility of taking no action. Now, different types of information in the consequence matrix comes from different sources. Some of the information comes directly from the stakeholder, and this is information related to the consequences associated with a false alarm, so unnecessarily taking a particular action. So the second type of information comes from a mixture of discussions with stakeholders and the earthquake engineering seismic performance assessment procedures. And this information relates to the mitigating effect of a given action, so how much the action reduces the impacts of an incoming earthquake. and therefore it's represented in the consequence matrix as the residual risk associated with a particular action. So how much that action does not mitigate the impacts of the incoming earthquake. Then the third type of information comes exclusively from our seismic performance assessment procedures. And this is information related to the case of taking no action. So it's the loss that would occur for our building in the given earthquake in a conventional seismic risk assessment procedure. The next step involves translating the consequence matrix into a decision matrix by accounting for decision maker preferences. So the decision matrix takes the consequence matrix values, normalizes them, and then weights them by the stakeholder preferences towards the different criteria. And the final step in our method involves taking the action that collectively minimizes the values across the different criteria in this matrix. And we want to take the action that minimizes rather than maximizes the values because all of the criteria are losses in our case. So we've seen how the consequence matrix gets translated into a decision matrix in order to determine the optimal action. Now the consequence matrix requires information from the earthquake early warning infrastructure on the seismological characteristics of the incoming event, which then gets combined with our seismic performance assessment procedures to translate this information into tangible consequences of the incoming event on the built environment. The consequence matrix also relies on stakeholder information, and this is also used to populate the decision matrix. We first apply our method to a hypothetical school located in Palo Alto, California. Now for this example application, we only have two possible actions and therefore two rows in our consequence matrix. We either trigger the alarm or we don't trigger the alarm. And we consider the three criteria that were discussed in previous slides. Now the question we're going to answer with this particular application is what is the optimal action as a function of ground shaking? And therefore, we're going to assume that the earthquake early warning infrastructure is feeding the consequence matrix with accurate and certain estimates of the ground shaking associated with the incoming event. Now we can run through the methodology for different values of possible ground shaking to develop a plot as follows, which also captures diverse stakeholder preferences towards underlying criteria. The plot shows on the y-axis the optimal action, either trigger the alarm A1 or don't trigger the alarm A complement, as a function of ground shaking expressed in the form of spectral acceleration at the building's fundamental period. Now what we see from the plot is that the optimal action for a given level of ground shaking can change depending on stakeholder preferences. So the alarm is actually triggered for much lower levels of ground shaking if a stakeholder prioritizes minimizing casualties than it is if a stakeholder prioritizes minimizing downtime, for instance. Another question we can answer with this type of plot is how often is the alarm triggered if we superimpose on the plot site-specific hazard information. And what we find is that the alarm is triggered around once every 10 years if the stakeholder prioritizes minimizing casualties, but much less often if the stakeholder minimizes prioritizing downtime. So this type of plot and these type of findings underline the importance of involving the stakeholder in earthquake early warning decision-making efforts. Now let's look at a different application of our methodology. We're going to focus here on the port of Giattaro in Italy. So in this case, we're not just going to be looking at one individual building, as we were in the case of the hypothetical school. We're actually going to be looking at a complex system of critical infrastructures which have a number of interdependent functionalities. The consequence matrix again consists of only two rows, either trigger or don't trigger the alarm, but we introduce a new criterion in this case, which is port performance loss, that measures the reduction in the number of containers that the port can handle, and is essentially related to the functionality of cranes within the port. Once again, we ask, what is the optimal action as a function of ground shaking, examining 5 cases in particular, the first 3 of which correspond to different stakeholder criteria preferences, whereas case 4 and case 5 correspond to simplified assumptions about the port's interconnected functionality. In case 4, we assume that the crane can function independently of the control office, whereas in case 5, we assume that the crane can function independent of any other component within the port system. So it's important to note that these are simplified assumptions. Again, we find that the optimal action for a given level of ground shaking can change depending on stakeholder criteria preferences. And another interesting finding is that adopting simplified assumptions about the port's interconnected functionality can lead to unconservative results, i.e., triggering the alarm at a higher level of ground shaking than we would if we assumed more complex and more realistic assumptions about the port's interconnected functionality. Again, if we superimpose hazard information, we find that the alarm is triggered around once every 100 years in the case of equally weighted stakeholder criteria preferences and more accurate assumptions about the port's interconnected functionality. So we conclude that the optimal action depends not only on stakeholder preferences, but also the level of assumptions that we adopt for the port's interconnected functionality. So in conclusion, we have developed a novel method for risk-informed earthquake early warning decision-making that integrates tools from earthquake engineering and multi-criteria decision-making. Through 2 applications, we have demonstrated that the optimal action, triggering or not triggering an earthquake early warning alarm in a given scenario, can change depending on stakeholder preferences towards different types of losses, as well as the assumptions we make on the underlying interconnected functionality of complex infrastructure systems. We're also in the process of applying this methodology to a bridge in the Pyrenees and a school in Patras in Greece. So this method ultimately allows us to determine the optimal action as a function of some information about an incoming earthquake. All of these computations can be done offline for efficient real-time decision-making when an earthquake actually happens. For more information, please see the publications at the bottom of the screen. Thanks very much for listening.